All right, we're going to start off the new session right now. We are going to have 3 talks in this session. My name is Jong Choi, Session Chair, University of Central Florida. Welcome to Orlando, Florida. This is my home ground. And our first speaker is Niklas from Hamburg University of Technology. He's going to talk about reconfigurable and updatable embedded systems. Then give it a shot, please.
Yes, thank you. My full name is Niklas Gollenstede, and I'm here today to present reUpNix and how we do reconfigurable and updatable embedded systems. But why would you want such a thing? Well, for example, it's really expensive to send stuff into space. So whenever we do that, we want to make sure that we get the maximum utilization out of any single thing we send there. For the computer systems embedded into satellites, this means that next to being super reliable, they need to be updatable and reconfigurable. Updatable so that we can react to changing requirements or that we can fix mistakes we made. Reconfigurable so that we can reuse the existing hardware for different tasks just by changing the software that's running on them. When we update a device, we load a new software version onto it, change execution to that new version, and eventually remove the old version. So it's a linear process, replacing old versions with new ones. For reconfiguration, we also want to change the software that our device is executing, but we want to, or the settings of that device. But we want to do that more frequently and faster with lower overhead than for updates. So instead of replacing old versions permanently, we want to freely switch between multiple concurrently installed versions. NixOS is a GNU Linux distribution that has a rather unique architecture. This architecture makes it especially suitable for reliable updates and efficient reconfiguration. But so far, NixOS is quite popular on server and desktop systems, but it sees very little use on embedded devices. So we asked ourselves, why is that the case, and what can we do about it? Let's start by having a look at NixOS in general. Integral part to the NixOS Linux distribution is the Nix build tool. You provide Nix with a formal system description of the desired system in Nix own configuration language. Nix will then take this input and build outputs according to the formal description. In case of NixOS, the output is a complete Linux operating system. While the formal definition is provided as one holistic composition, the output is actually broken up into multiple pieces. In Nix, these are called components. All of these components are stored side by side in a global directory at nix/store. Once written to the store, the components there are never modified. And each component in the store is named after a hash over its immutable content. Therefore, no 2 components of different content can ever be in conflict with each other because they just have different names. So when we provide Nix with a second system definition, it will build another set of outputs and can place those in the same Nix store. Where the new components are different from existing ones, Nix can always just store these under a different name. And where the new components actually happen to already exist in the store, Nix can simply reuse the existing components. Because the Nix build process always starts with a complete system definition, and because the Nix build process is designed to capture all inputs to a build, building a NixOS system is actually very reproducible. Further, the Nix description language is Turing complete, and NixOS provides many options for composition and customization. This makes NixOS very flexible. And finally, NixOS inherently supports reconfiguration because a single Nix store on a device can store multiple system installations, and each of those installations is derived from a composable and formal system description. But NixOS also has some problems that are critical, especially for embedded systems. For starters, its default installation size is rather large, hitting at 1.1 gigabytes. For reUpNix, we were able to reduce this to just about 155 megabytes. So we were able to remove 85% of the system installation size without much affecting its functionality as an embedded operating system. Further, for reconfiguration and backwards compatibility, it makes sense to support OCI containers. But existing OCI container integration in NixOS uses either Docker or Podman, and especially the Docker daemon creates some considerable runtime overhead. We were able to remove this by using systemd nspawn instead. Further, we can actually store OCI container images on our devices more efficient than either Docker or Podman can do it. Instead of using the classical image layer-based deduplication, we deduplicate the actual contents of the images on a per file basis. Another big problem of NixOS is that it tends to create quite large updates. We mitigate that in reUpNix by using differential update transfers. Finally, NixOS's bootloader is not actually created as part of the reproducible Nix build process. Therefore, existing bootloader implementations in NixOS are too fragile for reliable embedded systems. For reUpNix, we created a bootloader configuration that can be updated failure atomically. And we also integrated reconfiguration into this bootloader configuration. For the remainder of this talk, I will be focusing on the last 3 points: updates, the bootloader, and reconfiguration. So what makes NixOS updates so big? The components in Nix span a dependency graph. And by design, each component contains the name of all the components it depends on, at least once. So when we build a new system that changes the content of a component that's deep in the dependency graph, then that necessarily changes the content of all packages that depend on it, because those contain the name of that other package. Since that also then changes the name of this package, it yet again changes the next package, and so on. This ripples all the way through the dependency graph to the root of the graph. So in essence, this creates many new components when we do an update, and by default, NixOS would need to retransfer all of these components as a whole, which is obviously rather inefficient. But oftentimes, a component of very similar content already exists on the target. So to improve the efficiency of the updates, all we need to do is find that similar component before the update and then transfer the new component differentially based on that. Unfortunately, Nix components have no clear package identity. So it is generally hard to tell which of the hundreds or even thousands of components that you have installed on your device is closest to which other one. We therefore walk the pair of dependency graphs before and after the update and do a simpler similarity search on the local set of dependencies, which is much smaller. In our example above, we start with the root of these two NixOS systems and then just take the first dependency and do the local matching. In this fashion, we just recurse through the entire graph and transfer each of the packages differentially to the target. Now, since both the before and after dependency graph of the system can actually be known to the sender of the update, the sender can do all the diffs locally on its own. Therefore, the stream of differential updates can be transferred to the target unidirectionally without ever needing interaction with the target. This is just a small subset of the evaluations we did for for the transfer efficiency. Due to the time, I will mostly just flip over this. But the important point here is that when we do use bsdiff as the implementation for the diff function on the previous slide, we're actually able to reduce the overhead of the updates or the overall size of the updates by up to 99.8%, at which point it's really not much left anymore. Now, with the new NixOS system transferred to the target Nix store, we need to change the bootloader configuration to apply the update so that we can boot into it. Our goal is to do this safe and atomically for NixOS, and we want to do it independently of the hardware and the firmware. For firmware compatibility, the Linux kernel and init RAMFS of NixOS need to be stored on a FAT32 boot partition. So when before we just had one boot entry for our previous system, we can now simply create a second bootloader entry on that partition and update our system that way. Unfortunately, that's a really bad idea because writing to FAT file systems is not safe. If the write gets interrupted in midway, then our system can become, the file system can become corrupted and our system permanently unbootable. So instead of writing to the boot partition, we do AB partitioning, but we only do so for the bootloader partition, still keeping just a single system partition. Unfortunately, this also really only moves our problem because now we need to modify the firmware to tell it to boot this different boot partition. Since we don't want to interact with the firmware, we also now duplicate the GPT file table, partition table on our boot disk. And this now actually solves our issue because we can switch between the different partitionings on our system by simply overwriting the GPT header. And since this header only occupies a single disk sector on basically all flash media, we can do this in one atomic write operation. Yes, and a nice bonus about this is that it's not at all NixOS specific. This would also work for pretty much any other operating system. Right, finally, for reconfiguration. Reconfiguration means that we want to change the software that our system is executing, or we want to change the configuration of that software. This is quite similar to updating the system software, but updates have a slow and linear progression, where new versions replace old ones, whereas reconfiguration should happen faster and freely between a set of configurations. Recall that the Nix store can already hold multiple system installations. So to enable reconfiguration, all we need to do is two things. We need to get those multiple systems into the Nix store, and we need to have a way to switch between the systems we have there. The formal definition of each NixOS machine can define multiple variants called system profiles. These profiles can differ in small ways, like a single configuration file, but they can also differ significantly. For example, they can use completely different kernels. With reUpNix, each machine implicitly has a default profile. This is a safe fallback. It is very simple. It only contains SSH basically and no applications. So it is very hard to ever break this, but it is still enough to change into the other configurations and to do updates. We decided to only allow reconfiguration by rebooting. This ensures that the reconfiguration behavior is always correct and well-defined. That is, the system's runtime state after the configuration will only ever depend on the definition of this configuration and not on anything left over from the previous configuration. Further, rebooting is actually also the only way to achieve complete reconfigurability, since it is the only way to, for example, change which kernel we are executing. But if we always boot the default profile, how do we actually switch configurations by rebooting? Well, we do actually have a boot once functionality. On the booted system, you can execute a command that sets the next boot entry. And on the next boot, the bootloader will read that next boot entry, delete it, and only then resume the booting this next boot entry. So regardless of whether the boot afterwards actually succeeds or not, on the next boot, it will always boot into the same default system. That way you can never get stuck in a boot loop on a bad configuration. On UEFI systems, we could use an existing variable to do that. For U-boot, we actually needed to re-implement that using a combination of the compiled in and runtime variable boot configuration options. A drawback of rebooting for reconfiguration is that rebooting, especially on low-end devices, can be rather slow. In our experiments on a Raspberry Pi, a complete reboot pretty reliably takes 25 seconds, but we still think that it's worth it to pay this price and time for the correctness and completeness of the reconfiguration. Yes, and with that, I think you can read the conclusion on your own, and I would be ready for questions.
Yes, please.
Hey, so you spoke at the beginning about like the application to like sending into space and like reconfiguring. So did you do any testing regarding the reliability? So you talked about the atomic update of the boot system, but did you actually try to perform the update while introducing some faults into the system and see if it still works and if it doesn't break?
No, we did not. But the only thing that this requires to be atomic is that, in fact, the write of this 512-byte GPT header is atomic. And I think that's just something you can look up on your datasheet of whatever flash media you are installed on. And then, by logic, you can deduce that this is, in fact, atomic.
All right, thank you. Another question, please. Yes.
Please allow me some kind of ignorant question. So where is the location of the bootloader? Where is the bootloader?
Yes, overall it slightly depends because bootloaders tend to have multiple stages. Anything that's installed on the boot disk we would call, anything that's not installed on the boot disk we would call firmware in this setting. And we then have a second stage bootloader that is part of the bootloader configuration that sits on the boot partition. So on the boot partition, we have this second stage bootloader, which is either U-boot or system deboot for EFI systems. And we have configuration files for this, and we have all the kernels and init.rmfs's, which we need to then boot into our actual system. I hope
So
that
it can
answered the
be, can you handle the network bootloader?
I don't think that network boot is particularly applicable for our scenario. But probably, anything that eventually boots a partition from disk works for us. Because basically any firmware at least that is supposed to run a Linux operating system would sooner or later load something from a disk, right? And at that point, most of them are configured to boot either the AFI system partition, the first partition on the disk, or a partition that is flagged as bootable. And we don't actually only select, with a GPT table switch over, we change all of those properties. So as soon as your firmware is just remotely compatible, this should work.
Thank you for the question. Other question? No? I have one question. Maybe I can follow up the question. Of course, you partition the bootloader, and at least we have two different versions of the bootloader. Then can you expect size of the bootloader? So is it really small or large?
It depends. NixOS tends to build kernels that include a bunch of stuff, especially on ARM. So there, the kernel itself is rather big, and that needs to be placed on the boot partition, at least currently. But the smallest boot partitions we built, I think, were somewhere around 16 megabytes, I think. And that included the init.rmfs, a kernel, and U-boot, I think. Either 16 or 32 megabytes. So that's all that you duplicate, and then the rest of it will be this shared Nix store. So compared to an actual full AB partitioning, this is much more space efficient.
Okay. All right. Thank you for the answer. Let's give applause to the speaker.